This video will discuss solving rational inequalities. Like polynomial inequalities, there are two strategies to solving rational inequalities. You could graph the rational function and look at the picture. Any portions of the graph above the x-axis will satisfy a greater than or equal to inequality, and any portion of the graph below the x-axis will satisfy a less than zero inequality. Rational functions take a long time to graph, therefore I would never use this technique unless I was given the graph. We're going to focus on the second strategy, which is the test point strategy. The test point strategy for rational inequalities is extremely similar to the test point strategy for polynomial inequalities. You're going to start by writing the inequality, so 0 is on one side and there is a single rational expression on the other side. So if you happen to have a rational inequality that looks something like x over x plus 3 minus 1 over x is strictly greater than 0, you would have to subtract the rational expressions on the left-hand side first to make a single rational expression. Next, we want to identify the numbers that make the numerator or denominator equal to 0. So basically, we're finding the zeros of the numerator and the zeros of the denominator. Then we'll graph the numbers, the zeros that we found in step 2 on the number line. These will divide the number line into intervals. We'll choose a test point in each of those intervals, plug it into our original inequality to determine the intervals that satisfy the inequality. We'll consider the endpoints separately. So if it's an or equal to inequality, we'll include the endpoints, but if it's a strict inequality, we won't. Now there's one big exception. You see, anytime we have a rational expression, we're always concerned about the denominator being equal to 0. So you have to exclude zeros from the denominator regardless of the inequality symbol. That rule that a 0 in the denominator makes an expression undefined trumps the or equal to part of an inequality symbol. And then we'll write our solution set in interval notation. Let's solve x minus 3 over x squared plus 10x plus 25 strictly less than 0. Notice that we have a single rational expression on one side and 0 on the other side. So I want to find the zeros of both the numerator and the denominator. I'm going to start by factoring both the numerator and the denominator. The numerator cannot be factored. The denominator can be rewritten as x plus 5 times x plus 5. So we want to find the zeros from the numerator. Setting our numerator equal to 0 and solving, we get x equals 3. And then we want the zeros from the denominator. Setting each one of those factors equal to 0 and solving, we get x equals negative 5, and we get it twice. So really, we only have 2 unique zeros. So let's split up our number line at negative 5 and positive 3. What I like to do to remind myself that I have to exclude zeros from the denominator no matter what the inequality symbol says is I like to put a big X on my number line at the zeros from the denominator just to remind myself that I cannot include those. Now let's choose some test points. We need to start by choosing a number less than negative 5. I'm going to choose negative 6. I have a factored form, so I'm going to plug my test points into here and just use my even odd rule. Now, typically we use the even-odd rule for just multiplication, but it applies to division as well. We just haven't really talked about it before because rarely do you divide, 10 divided by 3, divided by 2, divided by 6. We don't usually do that, but even-odd rule applies here as well. So let's plug -6 into our first factor of x minus 3. That's going to give us a negative. Plugging -6 into our first factor in the denominator, x plus 5, I get a second negative. And then plugging -6 into my second factor of x plus 5 in the denominator, I get a third negative. Even-odd rule, 3 negatives, tells me that I'm going to end up with a negative. Now we move on to our next interval. Choosing a number between -5 and 3, I'm going to choose 0. Plugging 0 into our first factor, x minus 3, gives us a negative. Plugging 0 into our next factor, x plus 5, gives us a positive. Plugging 0 into our other factor of x plus 5 gives us another positive. So I have one negative and two positives. Even-odd rule tells me we're going to get a negative. Our last interval, we need to choose a number greater than 3. I'm going to choose positive 5. Plugging 5 into our first factor, x minus 3, I get a positive. Plugging it into our first factor in the denominator, x plus 5, I get a second positive. Plugging it into our third factor, x plus 5, I get another positive. 3 positives end up giving us a positive. Now we turn our attention to the inequality symbol. We want to be strictly less than 0. So what kind of numbers are less than 0? Negative numbers. So that includes this interval and this interval. Our inequality symbol is a strict inequality, so that means that we're not going to include the endpoints. So we'll have negative infinity to -5, not including, and then not including -5 to not including 3. The solution set to this rational inequality is negative infinity to -5, -5 to +3. Next, let's solve 2x squared minus 7x plus 6 over x squared minus 3x minus 4 greater than or equal to 0. Notice that we already have a single rational expression on one side and 0 on the other. So I want to factor the numerator and the denominator so that I can identify zeros from both. Our numerator factors into 2x minus 3 times x minus 2, and our denominator factors into x minus 4 times x plus 1. Finding the zeros from the numerator, we set each one of those factors equal to 0 and solve. We get x to be 3 halves and x to be positive 2. Then we need the zeros from the denominator as well. Setting each one of those factors equal to 0 and solving, we get x to be 4 and x to be -1. We'll break up our number line at those 4 zeros, remembering to put them in increasing order. And this time our number line has been broken up into 5 intervals. We'll start with our first interval, less than -1. Let's choose a test point. I'm going to choose negative 10. Since we were able to put this rational expression in factored form, I'm going to determine the sign by plugging my test points into the factored form and using our even-odd rule. So plugging negative 10 into our first factor, 2x minus 3, that's going to be what, negative 20 minus 3, negative 23, so that one's negative. Plugging into our factor of x minus 2, I get another negative. Plugging negative 10 into our factor of x minus 4, I get a third negative. And plugging negative 10 into our factor of x plus 1, I get a fourth negative. 4 negatives, following the even-odd rule, gives us a positive. I'll move on to my next interval, choosing a test point between negative 1 and 3 halves. I'm going to choose 0. Plugging 0 into our first factor, 2x minus 3, I get a negative. Plugging 0 into our factor, x minus 2, I get a second negative. Plugging 0 into our third factor, x minus 4, I get a third negative. And then plugging 0 into our fourth factor, x plus 1, I get a positive. 3 negatives and 1 positive, that's going to give us a negative. Our next interval, we're not going to get to choose as nice of a number because I need something between 1.5 and 2. I'm going to choose 1.9. Plugging 1.9 into our first factor, 2x minus 3. That's going to give me 3.8 minus 3, which is positive. Plugging 1.9 into our second factor, x minus 2. That's going to give us a negative. Plugging 1.9 into our third factor, x minus 4, gives us a second negative. And plugging 1.9 into our fourth factor, x plus 1, gives us a second positive. So I have 2 positives and 2 negatives. That's going to give us a positive answer. Moving on to our next interval, I'm going to choose a test point of 3. Plugging 3 into our first factor, 2x minus 3, gives us a positive. Plugging 3 into our second factor, x minus 2, gives us a positive. Plugging 3 into our third factor, x minus 4, gives us a negative. And plugging 3 into our fourth factor, x plus 1, gives us a positive. So I have 3 positives, 1 negative. That's going to give us a negative answer. Our last interval, I want to choose a number greater than 4. I think I'm going to use 5 this time. Plugging 5 into our first factor, 2x minus 3, gives us a positive. Plugging 5 into our second factor, x minus 2, gives us a positive. Plugging 5 into our third factor, x minus 4, gives us a positive. And plugging 5 into our last factor, x plus 1, also gives us a positive. So we ended up with 4 positives this time. The result of 4 positives is a positive. Now we turn our attention to our inequality symbol. X is greater than or equal to 0. Oh, I just remembered I did not X out my zeros from the denominator like I like to do. So I'm going to X out the zeros from my denominator to remind myself that I cannot include those zeros no matter what the inequality symbol says. Back to our inequality symbol. Our rational is greater than or equal to 0. So what kind of numbers are greater than 0? Positive ones. So our solution is going to include this interval, and this one, and this one. Okay. Our inequality symbol is or equal to, so that would mean that we want to include the endpoints. However, we cannot include any of the endpoints that came from the denominator. Our first interval would go from negative infinity to negative 1, but negative 1 was a 0 from the denominator, therefore we cannot include it. That first interval will be negative infinity to negative 1, not including. The second interval in our solution set is from 3/2 to 2. Neither of those zeros came from the denominator, therefore we will follow the inequality symbol and include both of those. And then our third interval from 4 to infinity, that 0, 4 did come from the denominator, therefore we have to exclude it despite the inequality symbol, and we're going to have 4 to positive infinity. Our solution set is negative infinity to negative 1, not included, including 3/2 to 2 included, and then not including 4 to positive infinity.